So, talking more about logarithms today, first thing we're going to do is to review some things we know about logs and use that to help us figure out what the graph of the log function will look like. And then we will work through proving or verifying the log properties that we've been using for a while. So first, a little bit of review here. What is the logarithmic form of this exponential expression? So I've got it with an exponent. How do I change it so it's log of something? Okay. So log base b of n equals L. Okay, so we know that much. Also, we've been doing some things with problems like this. If I have 6 to the log base 6 of 24, how does that simplify? Everybody shout it out. What does that equal? 24, we know that much cancels out and we just have 24. What about log base 5 of 5 to the 8? If we write it the other way around, what happens there? Everybody shout out the answer. And why does that work? When I have a log and an exponential, they cancel out because they are what kind of functions? Whenever things undo each other, what do we call those? Abby? Because they are inverse functions. So we're going to use properties of inverse functions to figure out what the graph of the log function looks like. So the log is the inverse of the exponential. What does an exponential growth function look like? Everybody draw one in the air. Okay, so we're going to take that graph of an exponential growth function and somehow change that around so that we have an idea of what our log function graph needs to look like. So to do that with the graph, in general, when we have problems like this that say find the inverse, what's been our strategy? You have one function and you're supposed to find its inverse. What do? Anna? You switch x and y around. So what that would mean if I were talking about a graph. If I have a point AB on the original, if I switch x and y, that means this point would have to be on the inverse graph. So let's do that to do our graphs. So instead of y and x, I've got the n and L here. So let's see, that means that L is my independent variable and n is my dependent variable. So y equals 2 to the x, n equals 2 to the L. We've done the exponential growth graphs. You just drew one in the air for me. We've done enough of these, we know. This goes through 0, 1, 1, 2, 2, 4, 3, 8, and we can connect it so that it looks something like that. Okay, now let's use this and switch all of those points to get my graph of the log function. So now I'm going to have my new n over here is going to be my independent variable, and L is going to be my dependent one. So instead of 0, 1, I now have 1, 0 on this graph. Instead of 1, 2, I now have 2, 1. Instead of 2, 4, I now have 4, 2. Instead of 3, 8, I now have 8, 3. Instead of approaching my negative axis over here as a horizontal asymptote, I need to approach these numbers going in the negative direction as a vertical asymptote. And that is now what your logarithmic function family graphs all look like. They're all going to start out, unless we've had some sort of reflection or shift, near the negative vertical axis, come up through 1, 0, and then gradually keep increasing out to the right. But then, of course, we can do any reflections and shifts, and we'll get to those later. Could you use this process to think about your graph of y equals 3 to the x instead of 2 to the x, and then be able to graph y equals log base 3 of x. You'd still have 0, 1 becomes 1, 0. But you'd no longer have 1, 2. You'd have 1, 3. So you'd have 3, 1. You'd no longer have 2, 4. You'd have 2, 9. So you'd have 9, 2. Does that kind of make sense? Okay, let me show you one other thing about these graphs. So here I've redrawn the exponential graph and the logarithmic graph, and I've drawn in that dotted line y equals x. How do those two curves, can you describe one of them compared to the other in terms of that dotted line? Does it look like a reflection? It's not drawn perfectly. Anytime you're doing inverses, not just logs and exponentials, inverse functions, their graphs are reflections over that line y equals x because we get them by switching the y and the x. That's why we have that reflection. So now you can draw logarithmic graphs. So the other thing we're going to do today is to prove those 3 rules for logs that we've been working with. So we'll prove it in general, but this one has some numbers in it just to help us remember what we're going to try to do. Log base m of 2 plus log base m of 9 equals log base m of 18, because we can multiply those. That's the product rule. A little bit louder this time with everybody answering. If I have log base 5 minus log base 2, what do I have to do? Log base m of 5 over 2, 5 halves, 2 1/2. And if I have 4 log base m of 3, that is log base m of 3 to the 4th, 81, whichever way you want to answer that. So let's prove these, and you need to copy this down because you are going to be asked these over and over and over on your problem sets, and so you want to be able to copy exactly what we're about to do. So show why, verify, derive, prove, they can use any of those verbs to ask you to do this. We're going to do a little bit of a trick. We're going to do a particular substitution as we prove these things. So the substitution that we are going to use, paper I meant to pick up on it. I like this one better. Okay, we are going to start off with, and we need to match the variables that they've got there. So we are going to take big M, and since this log has base b, we are going to let that be b to the, and then we're going to pick some letter that hasn't already been used in that equation. So I'm just going to say lowercase a. And then I'm going to do the same thing for uppercase N. I am going to let that be b to some variable that I haven't used yet. So I'm going to let that be c. Then I'm going to change each of those from exponential to logarithmic form. So that means log base b of big M equals a. And for the other one, logarithmic form would be log base b of, where am I, big N would be equal to c. Now when we are trying to prove these, and we'll do this also with trig identities later on, when we're trying to verify or prove, we're going to pick either the left or the right of that equation, and we want to write one big long equals string. So we're going to pick, on this one I'm going to start with the left, and we're going to say that equals something, which equals something, which equals something, which equals something, until eventually I get whatever's on the other side of the thing I'm trying to prove. So for this one, we will start off with the left, log base b of mn, and don't forget to put your equal signs in between all the different parts of this. Okay, so now log base b of, but now I know m I've got up here is the same thing as b to the a, and n I have up here is the same thing as b to the c. So log base b of. Now I'm just going to look at b to the a times b to the c. If that was my whole problem, how would I simplify b to the a, b to the c? Chloe? Not quite yet. You're getting ahead of us. Don't jump ahead. Right now, all I want to do is to rewrite b to the a, b to the c equals. If I had x cubed, x squared, what would I do with my exponents? I'd need to add them. So that's going to be b to the a plus c. So that's what I can put in here. And I really don't need parentheses around that. So log base b of b to the a plus c. That makes sense to everybody. Now, what were you thinking at first? Once I have just one thing in there, log base b of b cancels out, and this is indeed equal to a plus c. But a is log base b of m. And c is the same as log base b of n. And that means I started with log base b of mn equals, and I got to the other side, log base b of m plus log base b of n, so I have verified that. So everybody got that one down, so you can do that. You wouldn't have to do this part in blue, the b to the a, b to the c, and x cubed, x squared stuff on your problem sets. Okay, let's prove the second of our three identities. We're going to do exactly the same substitutions. I'm going to let m be b to the a, and n can be lowercase b to the c. So that means I can write these in log form. Log base b of m equals a, and log base b of n equals c. Then I start with either the left or the right of the equation. I'll go with the left. Log base b of m over n. I'm going to try to get one long equation string until I get to the other side. So log base b of, well, m is just b to the a, and n is the same as b to the c. So I'll keep log base b, and I'm just going to try to simplify that red part. If I had x to the 12th over x to the 10th, what would I do with my exponents? Subtract them. So just to simplify that, I'm going to say b, and I'm going to subtract the exponents, a minus c. Okay, everybody, now log base b of b, what happens? Cancels. So we are left with a minus c. But we know that a is log base b of m. And we know that c is the same thing as log base b of n. And that's what we wanted to prove. So I have one long equation string that starts with one side of what I want to prove, equals, until I get to the other side, so I have proven that. So you have that copied down. You're going to need it on homework sets. Okay, the last one is just a little bit different because it doesn't have quite as many variables in it. I don't have log base b of m and log base b of n, so I only need to do the substitution on this one. Let n equals something. I'm going to keep the same base b, And I can pick any variable they haven't already used, so I can't pick x, can't pick n or b. I'm going to stick with b to the c since that's what I used on the other two. Why not? Change that to logarithmic form. So log base b of n equals c. This time, just because I've done it enough times before, I find it a little bit easier if I start with the right side, equals, 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 until I get to what was on the left. So I'm going to say log base b of n to the x equals. Well, I know that n is b to the c, so I'm going to change this n to b to the c. So I have log base b of b to the c to the x equals log base b of, now if I have x cubed to the fifth, what do I do with my exponents? Multiply them. So that means I can do that with the c and the x. So this will be b to the cx. Log base b of b cancels because of the inverse functions. So this is just equal to cx. So I started here with what was on the right, and I'm trying to get to what's on the left. I'm trying to get to x times something. Well, I have something times x, so I'm just going to use my commutative property and get the x out in front where I know I need to end up having it. And then c, somewhere in this, c right here is log base b of n. So I'm just going to change that c to log base b of n. And that is exactly what I had there on the left-hand side. So I've finished my long equals string. Jack.
Can you explain to me why you switched, or you did cx equals xc?
Because I started with my right-hand side here. And I looked at where I'm trying to go. I'm trying to end up with x times something. So just the way this is, I want the x to be the first thing when I get to my final answer. So I just moved it so it could already be there. Okay, last thing for today. You'll have a few homework problems that ask you to sometimes rewrite things using these rules. So if I wanted to rewrite log base b of 12 using the product rule, that means I need to think of two numbers that multiply to equal 12. So Natalie, tell me two things that multiply to be 12. 3 times 4. And this says I can rewrite that as what? No, I've already got the multiplying. If I want to split that up, log base b of 3 plus log base b of 4. And I could do 2 and 6. I could do 1 and 12. Let's make it a little bit more interesting. What if I wanted to do a half? Half times what is 12? So I could say log base b of a half plus log base b of 24. However, there's some things that I don't want to go with. What about if I did -2 times -6? Can I say log base b of -2 plus log base b of -6? No? Why not? Why don't you like that, Casey? Perfect. The argument has to be positive. So we can't do that. Okay, let's see what we could come up with for quotient rule, still for log base b of 12. Two numbers I can divide and get 12. Okay, so 24 and 2, if we want to start off relatively easy. And that means we would do log base b of 24, and then what? Minus log base b of 2. And what if I wanted some fractions in this one? What if I wanted to say log base b of a half over something? Okay, let's see. I need a half divided by something to still give me 12, right? Which means I need a half times the reciprocal. So what am I going to need to use? Abby. So if I do 1 over 24 right here, is a half times 24 over 1 going to give me 12? So I can indeed do 1 over 24 right there, which means I have log base b of a half minus log base b of a 24th. And if I just ask you for it, you just have to do one way. But we're going to get to where we have problems where you need to figure out a way that's going to get something that will match up with something else in the problem to let you simplify it. So we need to know that there are a bunch of different ways we could do it. And last one, let's use the power rule. So log base b of, how do you want to rewrite 36 with a power? Maya. 36 is what to a power? Okay, easiest one is 6 squared. So that's going to be, Kyle, what goes on the other side? What if I wanted to do it as log base b of 1/6? What would the power have to be? -2. No negative argument, so I'm fine. So I could say that's -2 log base b of a 1/6, and so on. So any questions from you guys on that? Okay, then I will let you get to work on this homework.